everyone. My name is Mohammad Awad. I'm a PhD student working with Dr. Nakmani.
My name is Mohsine Taarji. I'm a PhD student in electrical and computer engineering. So today our presentation is going to be over an introduction of neural network. So our outline will be, we're going to start with an introduction of neural network. We're going to do a small application to show how neural networks work. Then we're going to go over a diagram of neural network architecture, type of neural network, type of neuron, examples of neural network. Then we're going to go to the training, how we train the neural network. We're going to do first classification of learning method, supervising single layer, supervised multiple layer. Then we're going to see what is the advantage and disadvantage of a neural network. So as we see on the picture, this is a global idea of neural network. If you see, it's working as our brain. So first, there is an apple, and it's go over the brain. We have already some data that it's already classifying which one is the apple. Same thing for neural network. We have already some data, and it's go through that network to define what is the output. So we see here there is an apple, then it's trying to choose from the trained data that we have. There's an orange, then on the end it defined it as an apple. So here there is an experiment that's been done in 1995 that's explained the idea of neural network. They took a pigeon and they put it in a box and they gave it two different painting artists. It was Van and Chagall, and the pigeon has to recognize which painting it is. They train it, they show it all the painting of that certain person, and they reward that pigeon with some food. So every time they show the picture, they reward. So what they find is those are two different painting persons. This one, those two. So they train on the same one. So when they train on the same one and they show the person, that pigeon, the same pictures from the training set, it recognizes 95%. So the accuracy was 95%. But when from the same painter, they show his work, but the pigeon never saw it before. So the accuracy was 85%. So they never trained on the picture, it showed 85%. When they trained on the picture that the testing was on the same picture, it was 95%. So that's how the neural network works. So when you train on the test on the same training set, you get high accuracy, and when you train on different, you get lower accuracy. So here it's a global diagram of neural network. As we see, we have an input layer, hidden layer, and output layer. The input layer can have multiple inputs. The hidden layer can have multiple hidden layers and multiple nodes, and the output can have multiple nodes. The hidden layer, it can have one hidden layer, we call it shallow, and if it has multiple hidden layers, we call it multiple layers. So, yeah. So this is some, for the decision, we need to know this thing. We need to know the number of hidden layers. We need to know the number of units per hidden layer, the neurons. We need what type of activation function. We will talk about it later. So we have multiple types of neural network. There is single layer, feed-forward. We have multiple layers and recurrent. The first thing we're going to talk about single layer. What is a single layer feed-forward? So as we see on the picture, we have inputs and we have outputs. All the inputs are connected to the outputs. So that's why we have multiple inputs and multiple outputs. For multiple layer, we have a hidden layer. It's additional, that's a hidden layer. All the inputs, same thing, they're connected to the nodes of the hidden layer, and all the hidden layers, they're connected to the output. And that's recurrent network. As we see, we have input, hidden layer, and output. As we see, the only difference is that the output is connected to the input with a delay. And we see that we have also a hidden layer.
So let's talk about the node or the main unit inside the neural network. As you can see, let me go back. Here, the node is this. Sometimes it's called neuron or nodes, which is like the basic unit of the neural network. So what's the idea behind that? The idea is that you got different neurons connected together. So that connection is called like the weight. Like for this case, is the input connected to this neuron by like a weight, which is the see how much this input affects the main, this node or this neuron. And there's something else which is the bias, which is if you want to shift the output up or down. We have another figure in the next slide. Then we have the activation function, which is after you find all those parameters or the effect of different nodes to this node, then you put it through an activation functions to like kind of normalize the output or have a different shape of the output. And that will give you the output from that node. And here's the general equation used for the node, which is like the weight or the sum of weights times the input, then you add them plus some bias. Then you pass that through an activation function. So what is the weight? As we said, the weight is like a connection between one node to another, or like the input to that node. Usually the weights they are set between like -1 and 1. And there's like two types of like neural network based on this way. One is fixed networks. Like for example, if you have a model, your model, you can set those weights as fixed. Like let's say you want to have a model that predicts the price of a house. Like the number of rooms will have like effective like 60% of the price of the house, and the area will have an effective 40%. So you set up your weights before based on those predictions you have. So you don't have to for this example, you know the weights previously and you know your model. But for the next one is adaptive network, which is you don't know what's your model. You have like a black box. So you feed it some data and you let the network learn based on this data and update the weights. And we're gonna learn about this in the later sections, how the network update the weights. Then the bias. As we said, we have some connection between one node and another. And we know like it's a linear. Most connection like it's a line connection, which is like you start from that goes from negative to positive. Then what if you want your values to start from all of them not going to negative, start to like from 0 and up. So you can have a bias of 1. So you shift your signal, your V, which is called like the induced field. You shift it up by some bias, so the output from that node never goes down. All those parameters depend on your application, whatever you want from that node. And there's some types of nodes or some activation function, which is linear function. Like this node is related to this by a linear function, which is called like linear neuron. You have like logistic neuron, like a sigmoid, or perceptron, which is basically like in the brain, yes or no. This node either make this one fire or no. Or this one has like a yes and no. It's like an AND gate or gate, like a logistical gate. And here's some more examples of activation functions. We talked about this perceptron. You can make this go from like 0 to 1 or -1 to 1. Linear, which is 1 to 1 like relationship. We have piecewise, sigmoid. This one we're gonna focus on this one because this is the most used one, which is the sigmoid function, or like some people call it squishing function. And let's look at typical. This one, yeah. So let's to better understand the network, let's look at like a single neuron calculation, a single neuron example, so we can better understand it. Like for this example, take this neuron. Here, those numbers represent the weights going from this node, or this could be input, or this could be a previous node. So this is input to this node, or to this layer. We have weight for this one, they are connected by 0.25 weight, and for this node, or the second node, they are minus 1.5. So the way you calculate the value for this node based on the previous nodes is you take into account all the nodes. You start from this one, you get 1 here, then you multiply by the weight, then you add the next node or the next connection to this node, which is 0.5, and multiply by -1.5. Then you sum them, and you get the field that we talked about, the induced field of V, which is 0.5. Then this value you take and you pass it through your activation function, whatever activation function you have. In this case, it's yes.
No, it's not really a question. So it is possible to add something if I've taken out something into
you mean?
Since, like, by the time it's explaining something, if I have something come up in my mind that can add to to clarify,
Sure, you can ask.
okay, or add something.
Yeah.
Okay.
The-
No, you
No,
go ahead. Continue.
So we take our value, or like, let's say the v value, then you pass it to whatever activation function we have. In this case, it's the sigmoid. Then we get a number which is the value for this node. Then we do this process, same for different nodes. Then we carry on to the next node. So it's like a network, like a bunch of networks connected together. So you can think about it to better understand it. Just think of just simple node to better understand what's going on. Like this is another example. Like this is like a multiple layer, one hidden layer network. We have here the output from this H. We calculate them from the input times the weight for that one. Then you add the bias and you pass it through the sigmoid. We get some numbers here, which is values for those nodes or in that hidden layer. Then you do the same process. You take those will be your input for this layer or for this connection. Then you pass it with the weights here. You calculate the one here. Then you do the same thing. All of those will affect this node, and all of those input from the hidden layer will affect this node. So we get the similar equation, but the difference is the input will be the previous layer. Like if you look at this one, how many different variables we have in here, or how many different variables? Does anyone know how many? By looking at this network. So here's like if we look at this network, we see like we have 4 plus 2 neurons. Like here we got those nodes, we got 4 and 2. Then for each one of this layer we have 3 weights, and here 3, 3, 3. So we have 3 times 4 the weights here. Then we have here we got 4 inputs, so we'll have 4 weights go to this one and 4 weights. So 4 times 2, so we get 20 weights. Then for each one we can have a bias. Most cases you can have bias 0 or 1. So we have 4, then 2, which is 6. So in total we have 26 learnable parameters or variable. Like for simple networks we have 26 different parameters. And that's why we need an algorithm to learn all this. And that's what we're going to talk in the next sections. Yeah. And here's an example for the same network. How we're going to pass data like from this layer to this layer. Like a simple example. Like we can think of this network as like a matrix multiplication, which is we set up like an input as a vector, and we take the weights for each, like those weights, we put them in a row for each node. So this row will represent the weights for the first node, then second, third, and fourth. We set up this matrix multiplication, multiply those, we get a value, then add the bias, then pass it through the sigmoid to get this value. So to better understand it, first you understand how the single node works, then you can do like matrix multiplication to make a computer does it. Like in MATLAB, we will do most of the matrix multiplication easily. Then how we can let the machine learn our data. So and there's like mainly 2 different classification of learning methods, or 2 methods used. Like the first one is unsupervised, the second one is supervised. I think
question.
Yes.
Yeah. Now, it's just a question. Just add something, and if I can. Yeah, go back on the activation function. Yeah, they use the sigmoid activation function, but actually there is a way. The sigmoid, it is a contribute function.
Yes.
But you can also use a discrete function, because you can get that the function going from.
We talked about it. There is different ones. That
Oh,
you
Here's
can
the function.
it's not
Okay.
only one. It's different one. And you can.
Most people use the sigmoid.
Okay.
Yeah. Then we can talk the different functions based after the gradient descent with some limitation of sigma. Like I think Jose talked about the supervised and I think unsupervised, which is basically for our learning, like, we let the machine choose different clusters or classes, and then try to teach the network based on the classes that machine determined. Like, it separate the data based in cluster, then try to do the learning based on those. And this is like an unsupervised learning. But we're gonna focus on supervised learning because most people use supervised. And what is it? The difference, we teach or we give the machine the classification. We tell it, like, here's the data, and this is will be like Mohsine said, this is apple, this is orange. We give different picture of apple, different picture of orange. We tell it, this is orange, this is apple. Then we try to teach it, and we'll make the decision based on the parameters it learns. And here's like a simple or general idea behind the supervised learning. The main thing, as we said, we feed it the data we have. Let's call it patch. We do like, first in neural network, we have something, the weights. And we don't know those weights. We wanna like make the machine determine those weights. So first we initialize it randomly. We do a forward pass, which is put our input, pass it through the networks, and get some data. Then we find the error for that. Then we do something called back propagation. So we go back and update our weights based on the error we have. Then we do the process again. We feed the same data, then find the error, the new error we have. Then we do the back propagation. We update the data, then we do it again. So we feed the data, get some number for our network, then we compare it to the actual data that we tell the network this is the correct data. Then we update the weights based on this with some function or optimization functions. Then we keep the process until we reach an error that it's satisfied error, like a small error. We can define it before we start the learning process. So the main principle for the network and neural network, artificial network, is energy minimization, or as we said, error minimization, which is reducing the error for each node in the network. So we have a better like classification functions. And to do that, I think we learned about the gradient descent, which is basically minimizing our function or finding the local minimum of any functions we have. Like in gradient descent, we have a function. We want to see the minimum value. Like for our case, our function is the error. We have like error function like this, and we're trying to find the global minimum, which is the lowest error we have based on the W we feed or the W we use. So here's the equation for the gradient descent, which is we start with initial value, then we update that based on the derivative of our function times some learning parameter, which is in most cases called the step size, or how much this will affect our initial guess. And I need to mention one thing. This is based on the derivative, so we have to use like a differentiable function for the gradient descent. And the advantage for this is, first, it's very easy to implement and it's scalable, and you can find the minimum value effectively. Then some disadvantage, as we can say, might get stuck in the local minimum, or if you choose different step size, maybe if it's too small, will take too much to reach the minimum. Too big, maybe miss the global minimum. So you need to sometimes experiment with the alpha value to reach the optimum, or to reach the minimum you desired. And as we said, this function, the gradient descent, only works in differentiable function, like sigmoid. But if when I use the perceptron, like this is the sign, which is like logistic yes or no function, it's not gonna work because it's not differentiable. So most people use the sigmoid. It's much more common. Now, how we use the gradient to update our weight, or how to minimize the error. We know that let's look at a simple case, which is like one neuron. We know we have X, we have W, which is the weight. This is input. Then we have the output, which is just the sum of the weight times the X. So if you look at the back to the graded descent, we know that we have the value, then initial value, then another initial value equal. This is not initial. This is the new value we need to find, which is just initial value minus some step size times the function. For our case, because we want to minimize the error, we said we need to minimize the error and we need to update the weight so we can minimize the error. So what is this term? To better understand it, we need to use like the chain rule, which is, if we look at our simple example here, we know that we have like dE over dy, which is the error. We can set it to be like just a differential error, which is y, our output value, minus d, which is the actual. Then we know our function y, we can represent it in terms of x, which is w times x. So we can do a chain rule, first derive our function, dy over dw, which is just x. Then do the dE over dy, which is just the error of our system. And when we feed it back here, which is this term, it's going to be just minus alpha, then y minus d times x. So this is the difference in the weight, or to update the weight, we need to find this term, then add it to the previous term, and keep doing that to reduce the error. And this is called like a delta rule. For the book that we have, they used like, here there's a plus sign. They use it because they define the error differently. They defined it as d minus y. For the function is originally y minus d. So you need to make sure from those signs. And for that function, this is, we're assuming that we're using like a linear like activation function, or there's basically no complicated activation function. But if you want to add an activation function to this term, like in this case, we add activation function here, and we change our symbol model by adding activation function. We get y, which is the output, will be like phi v, which is first taking v as we defined it before, which is w times x, the sum of w times x. Then we plug that into the activation function to get our output. Similar as before, we need to find d. Where's that? Where's that? Okay. Similar as this one before, we need to find this term, dE over dW, which is our function. We need to plug it into the gradient descent to minimize the error. So if you use the chain rule, we can have like dV over dW. Same thing, this will be x, here's v. To differentiate this in terms of w, you get x. Then dy over dv. What is dy over dv? We got this, y will now be our activation function. So this term will be basically just the derivative of our activation function. Then this term, as before, is just different in the error, which is y minus d. But for the book, they flipped it. They used d minus y, so we add plus here, and we get those terms, which is this x from this derivative, then e from here, and derivative of the activation function, we get it from this term. And we get like something called generalized delta rule, which is a rule to update our weight based on our error, which is, they call it delta, and this is the update function to update the weight based on our error.
So we saw over here that we have to use the derivative of the phi. So over here, so the derivative of the sigmoid function, we're going to do some simple math. So the sigmoid function, it's 1 over 1 plus exponential of minus x. If we take the derivative, that's going to give us exponential of minus x over 1 of, that's some basic derivative. So what we find, that's the derivative, it's equal to 1 plus exponential of minus x over 1 plus exponential of minus x squared. minus 1 over 1 plus exponential of minus x squared. If we see this one compared to the phi that we have, the original one, what we see? This one we can take 1 over exponential of minus x. We have 1 over minus x. We see it phi minus, and this one is phi squared. Same thing, and that's what we did over here. So if you factor with phi over here, it's going to give you phi factor to 1 minus phi squared. Phi. So that's what we got over here. So if we go to delta function, if you see over here, so delta function is equal to phi prime, or the derivative of phi multiplied by the error. So we're going to replace the phi prime over here on this equation that we saw earlier. And what we get phi multiplied by 1 minus phi multiplied by the error. And if we go back to the equation, the generalized for the delta rule, so we replace everything. We replace the delta over here, and our delta is this one. So it's going to be omega plus alpha multiplied by delta multiplied by the error. So this one, it's a neural network training example. So we have two inputs, so we get omega 1, omega 2, and we get an output. It's an AND gate. So we're using the signal function. So if we have two inputs, 1 and 1, and our weight for the first one is 0.1, and the weight for the second one, it's the 0.2, and we have the bias, it's 0. So what's going to be the calculation? So it's going to be the weight multiplied by the input, the x. So the v is going to be 0.3. So what we do for the sigma function, we replace the v over here, so it's going to be 1 over 1 plus exponential of 0.3, which is going to give us our sigma function, which is 0.423. So how to calculate the error? So this one, the error, it's d minus y. What is the d? So the d, it's the actual output that we want. And our actual output that we want is 1. What is the y? The y is when we do the neural network, we get an output. So that's how we calculate the output, the error. We do the actual output that we need minus the input that we get. So we have the actual output that we want, it's 1, and minus the one that we got from over there. So it's going to give us 0.575. So when we do this one, we have to go to the generalized data rule. We got the phi, and we got the error, that's right? So we just do simple math. We just replace, if we see over here, we get the sigmoid function, and we got the error over here. So we just did the simple math. If we replace the phi and the error, we get 0.140. So what is the update weight? From the equation, it was the weight equal the old weight plus alpha multiplied by delta x1. So what is the old weight? If we see for the first one, it was 0.1. The old weight multiplied by the and plus, yeah, the alpha was 0.1, I think, and the delta we calculated, I think it's over here, 0.14, and multiplied by the x1, which is 1. So we get a number of 0.114. For the second one, for the second weight, if we want to update it, we do the same thing. What is the old one? It's 0.2 plus the alpha multiplied by 0.1 for the delta and multiplied by 1, and we get 0.01. That's how we update the weight of each one. So if we want to train on single layer, so if we see here, that's a single layer diagram. We have input and we have an output, and we see that each one has a weight, different weights. So what is the steps to train a single layer? So first, we have to initialize the weight, and there is two methods. It can be updated or it can be constant. So the second thing, we have to calculate the error. Second thing, we have to calculate the weight. Then over here we adjust the weight as we calculated just right now. Then we start repeating till we get satisfied with the results. So there is the schemes used for the calculation of the weight. So we have three different ones. So we have the schematic gradient descent, which we call it SGD. We have the batch and the mini batch. So we're gonna look at the SGD. So as we see over here, the SGD calculates the error for each training data and adjust the weight immediately. So if we see over here, we have different data. We have, like for example, we take 100, okay? So we have to take just one from 100. We go and we adjust the weight for each one. So how many times we have to adjust the weight? We have to adjust it 100 times. So it takes longer time to do this training. So we're gonna implement this in MATLAB. So we're gonna use a sigmoid function, and we're gonna use, as we see the error, we calculate it as the output error minus the one we get, and we're gonna, actual error minus the error that we get, and we're gonna do a single layer. If we see over here, that's the results that we're gonna get. So let's implement it on MATLAB.
Wanna talk about it? We got here X, then here's the actual data. Then first you initialize the weights. You do random in MATLAB. Then
Just to get the weight.
this is number of epochs, or how many time when a
Training
Training.
data. Yeah, training.
Sometimes it will be useful if you set up like a breakpoint of we check the error and we break it, but for simplicity we will train it like 1,000 times. We keep updating the weights for 1,000, not 10,000 times. So if you run it, you get, here's the actual D and here's the Y. So you see it's a high accurate, and
And we see that
you get error, it's very low error.
So over here it adjusts the error every time, and that's why we got the error very small.
Not sure if you jumped up there, but I'll discuss this more.
So second thing, we're gonna go to the batch. So the batch is different than the SGD. Instead of taking each one at a time, we're gonna take the whole data, and we're gonna adjust the weight. We're gonna take the average of the whole thing, and this is the function of the calculation. We took the sum of the average of the weight, and we're gonna, when we implement it on MATLAB, we're gonna use the same thing. We're using a sigmoid function. We use the same calculation of error, and we're still using the single layer. And if we see the results, it's gonna be close. We have 0, 0, 1, 1, and we have the same thing.
You go down, there's same parameters, but different is used in different functions. Here's the function, there's
We see we're using
Delta
sigmoid
patch.
function.
this is after we got the data, we run some sample data on it to test to give us the right output. Then check the error. See the actual, then it would give this similar result to that method here, which is 0.99.
So the actual output equal to the output that we get, and the error is very small. And the third one, it's gonna be the mini batch. So the mini batch, instead of taking the whole data, we just take a sample. So for example, if we have 100 training data, and we take in for the mini batch, we take just 20. So how many times are we gonna change the weight? We change it only 5 times. Because you say 100 divided by 20, so you only change the weight 5 times. And next we're gonna test the SGD versus the batch. Which one is faster, and which one, what's gonna be the best one to choose. If we can, I can explain the graph before we do it. So we see over here, that's the SGD and that's the batch. We see that's the SGD, it's get to the data before, so it's faster. But the only issue, it's gonna take more time. So it's time versus the
Processing. Takes more
yeah,
processing.
processing time. So it's faster, but it takes more processing.
Because we do that derivative more times.
So let's
So this one-
implement it in MATLAB.
Sure. SGD. It's same thing. We'll take data, then do 2 different weights here, then train them one time on the delta, the next time on the patch, and see the error. compare the error. Each time we will record the error and see what's the error after each epoch or each training run. So if you can tell here,
That's the same plot that we showed
the
earlier.
same,
Yeah,
like
the
SGD
is faster.
after like 100 time updating the error goes much lower than 100 time when you do the patch. So it converges faster than the patch method.
So next thing we're gonna see what is the limitation of the single layer. While we have a multi-layer. So here it's just a simple example of a single layer. We have, as we talked about, inputs and outputs. If we see we have 3 inputs and 1 output over here, and we have 4 times. So over here we're gonna talk about why do we need the multi-layer. So over here, linear separatable. If we see that it's separating into zeros and the 1. If you do the AND gate, it's separating them. But on the XOR gate, when we do the linear inseparable, we can do the same thing. If you take a line over here, you're not gonna get ones on one side and zeros on one side. We're never gonna get them together. So that's why we're gonna do the next layer. So this one we're gonna test the single layer on the XOR. So we say if we do a line over here, it's only gonna get 1. So it's not accurate. And that's what we're gonna see in this example. Here we're gonna see the result. We're using the same thing, the sigmoid, the error, and the single layer. And if we see the output, it's wrong. Yeah, that's the output, but we see the actual output. We want a 0, 1, 1, 0. But what we get half, and about. So we don't get like 0, 1, 1, 1. And that's what we're gonna implement on MATLAB.
So if there's a code called test delta XOR, which is the single layer. See, we get a huge error here, and this is the value.
So the actual values that we want
Like
is
if we
0,
try to train this example on single layer, it fails. The networks never converge. It can't find like actual weights value that can predict your input. Predict your output. Like this is the most common example, which is the XOR, which is this is the XOR, which is, as Mohsine said, it's not linear separated. So for the most limitation of single layer networks is it cannot do anything more than linear separatable data. Like you can see here, you can class the data into one class and another class. Here we have class here, and class here, class here. So the single layer can't like differentiate those data. You cannot like you drew something. If you imagine this as drawing a line through the data, you cannot do this. The single layer only can do like linear separated whole data, like the AND gate, as we saw before. It predicted the results like accurately. Unlike this, the XOR, it cannot predict this. This is more example.
So this one, if we see for the single layer, it's only classify one class. It didn't classify. Usually it has to do both of them. But for the single layer, it's only classify one. As we see it for 2 layers, if we use the middle layer, it's classified them both. If you use small layer, it's gonna classify them more classification.
For this example, they use the perceptron. Like to better understand this, they use perceptron and see how the effect of layers on the training of the data. So you can see if you use like one layer, you can't have much separation. Like just you can detect linear separated data. That's why people start using like multi-layer or 2 layers, 3 layers to have more classes, more separation between classes. Yeah. Then we're gonna talk about multiple layer networks. Continue. I don't know. We went too fast. We were gonna take a break, but keep going. So we saw the need for multiple layers. Now we're gonna try to learn or teach the networks on multiple layers. It's similar to single layer, but there's some small differences. Like this is an example of a multiple layer. We have like 2 layers, and we want to try to do the training on multiple layers. For like learning purpose, be easier if you choose a simple network. Like for this one, we have one hidden layer, output layer, and input. Each node is connected by a weight. Like this is 1, 1. The first one is represent this node. 1 is here. 2 represent this node, and 1 here. We use this notation. It's simpler to put it in a matrix form. As we said, like we put each row represent the weight for the input for that node. So it will be better if you flip those. You do 2, we represent this node, and 1 represent the input. It will be easier to represent it in matrix forms. So as we said, first to train the data, we need to random initialize the weight, then do a test pass or run the data through the network. For our case, we have like 2 layers. First, we do the first layer, then we do the second layer. For the first layer, we can put it in a matrix form. We take this weight, go through node 1. Here those going through node 1, and multiply them by the input and add them, which is just matrix form. When you do matrix multiplication, you multiply this row by this column, then you add the element. You get 1 element here. Same thing for the next node. You do the weight, which is weight for this node 2. This is weight 2. 1 coming from the input 1. This is coming from the second input. So you put it in matrix form, multiply them, then add them to get the value for that node. For the value, the V value, the field value. Then you put it through any activation function you have. For our case, if you use sigmoid, you put it through the sigmoid function or activation function, you get value. Then you do the same thing for the value over here. So you get something called like y1 parenthesis 1, which is the output from the previous layer at this point. Same thing here, y2 parenthesis 1, which is output we got to this node, this layer, the node in this layer. Then, as we said, we take the values we got from the previous node from here, we use them as input for the next layer, layer. So we take here's all our nodes. The input value will be the same thing, same equation. This instead of x1 will be this, which is y1 parenthesis 1. Same thing here, y2. Then the weight, same algorithm we use, or same method, which is we take the weights going through this node, put them in a row. Same thing here. For doing like a notation, as we said, we do. This is node 2, so it's going to be 2 here. Then 1 coming from node 1, so it will be simpler to represent it in a matrix form. We find the V values. Final step, we find the values. We put those values through the activation functions, and we get the final value of our network, which is y1 and y2. So first, as we did in the single layer, we pass the data through. We get the value. Then we need to keep record of those, the output, and those output, because we're going to use them in the backpropagation learning. So then we found the values. Now we need to find the error of our network. We know this is simple. We used this before, which is just error. The error from the network, which is E. Each node will have like its subscript. That this one E1, E2, which is D, the actual value we know for this node, or what we expect this one to produce, minus what we have from this pass-through. Same thing for the next node error. We will call it E2, the value we expect minus what we got. Then we do the generalized delta rule, which is the equation we have before. We put E times the derivative of the activation function times V. This V1, which is the V we got here at this node. You need to remember it's this. It's those V. We take those and we plug them into the generalized delta rule. Then we do something called backpropagation, like taking the error from here and we try to pass it to the previous nodes. Like the way we do it is like for error where's that one? Error here, which is the error here will be affected by this node and this node. So the way we do it, we take the sigma from this node multiplied by this weight, then we take this sigma multiplied by this weight, and we add them together. We get like an error for this node. And then we take this E, or the error, and we do the same thing, apply it to the delta rule equation, and we use the derivative of our activation, and we use this V, or this value, which is the value for that node we got from the forward propagation, or the first pass we did, which is this value. So we found all the errors terms, or how the network performs. Then we need to update our weight based on this, or use like the gradient descent that will try to drive our network to change the weights in the direction of the lowest error we have. So after that, we adjust the weight. We go to every single weight, and we plug like in here. We got this weight. We apply this formula, what we have before. This is the original weight value, and we get an updated weight value. And this is delta weight, which is derived from our delta rule. And to better understand it, we have an example here. Like for this example, if we want to update this weight, which is W11, we know our X, it's going to be just X, because it's the input from here. Then the sigma, which is, we found it before from the previous, this sigma we found it from the delta, or the error calculation. We plug it in here. Then alpha, which is the step size. This is, we can choose any step size we want. So this is, it looks similar to the training on the single layer. But, yeah, this. For this one, we do the same thing. For each node we want to find it, we need to find X, which is the input. Like for this one, X will be this, X2. If you want to find like the weight update for this W, it's going to be, if we take this X, and the delta will be this one, because here's the connection. You think of each, you look at each W you want to change, and you take the input, which is X, and you take the error from the sigma, from the table we have before, then you plug it into the equation. So it looks complicated, but it's based on like a simple math, or a simple like calculation. Same thing here. We have the sigma here, which we calculated from the forward propagation. For our input here, we get it from the first forward propagation, which is, as we said, y1 parenthesis 1, which is here multiplied by the sigma here, some step size or learning parameter. Then we update the weight we have. So, and we keep doing that and keep doing this process as we did in the single layer, and checking the error. Then updating the weight, checking the error, updating the weight, checking the error, until we reach like a low error that will satisfy our requirement for this neural network. And here's everything we said in stepwise. First, as we know, we have to initialize some random weights. Then we do a forward pass of our network, find the error, find the delta, because we're gonna use the delta rule to update the weight. Then you back propagate it to the previous nodes as we did. We take from error here, we go to delta here, and delta from the previous node. So if we have like even 10 nodes, we do the same step. We first start from the output, find the error, and we keep going down and finding all the deltas for all the nodes. And we do the update for the weight same way. Now we do the same method. Update the weight after we find that. Then we keep repeating that step until the network is trained. Yeah. And now let's go back to our example, which is the XOR example. As we saw in the single layer. Yes.
Okay. When you on the single
layer,
you have a bias, bias, right?
Bias, yeah.
Bias, yeah. But on the multiple layer, we don't have any bias.
No, there's a bias, but for simplicity, we'll never use it. It's hard to add a term in here.
It's zero.
We use zero bias. For all of them, we set the bias to be 0. Sure said that.
Yes.
There's a term, a bias term you have.
Okay.
But if you look at the derivative, it's bias. We set up the bias 0. Like for this example, set up the bias 0. It's easier to calculate if the bias is 0.
Okay, you choose the best.
Yeah, you choose the bias.
But
You choose everything, even how many nodes you want to have, and how many layers you want to have. All, I think there's maybe Dr. Ari can.
yeah, but on the
Yeah.
one with the
Give you-
matrix, we add the bias. If you go back one.
On the matrix.
Yeah,
Because
on the matrix, this one.
This is like an example. If we have a bias,
See, this
Forward
one, we
there.
added the bias.
yeah, you need to add the bias because
it's 0. For the other one, is 0.
Yeah.
The bias.
It just shift your thing either up or down.
If you look at the derivative, when you derive the, where's the like derivative here, even if you have, I think we're deriving based on W, so you only end up with X. Even if you have bias, your derivative will leave the X terms. For when you do the gradient descent, we're only going to use the X term because of the derivative.
Look, you always can use bias as additional weight, and your input will always be 1.
Yeah.
So this is the same thing. You can think about that matrix W as including bias already just with one more input. This input is constant 1, always. And this B coefficient will be just Wn plus 1. Like weight n plus 1.
exactly.
They multiplied by 1.
Okay.
Which will be just B.
Yeah, but for this network, we set the bias to be 0. It's not going to have a lot of effect.
Okay, so if I understand, so it is better if you have one layer, you add a bias to avoid 0, for example. But a multiple layer.
So you're not adding it. You're just assuming that your input is like your input 1, which is your external additional input, is multiplied by
Yeah,
0.
it works.
But you can train that B. So B is part of the training set. So you need to find such a B which will give you the solution. And the idea is that you have multiple different possible weights which all will produce the right answer. Right? So you would have like infinite number of sets for W1, W2, W3, and so on, and B, which will all produce the right answer.
Okay.
But you want to train it with the simplest set.
Yeah, so you
And
don't
they assume, for simplicity of the example, they assume that let's remove one of the parameters that we can train, and we'll train only the other parameters. They still will solve the problem somehow.
yeah, because
If not, then you need to add the bias.
yeah, and then that add that that made the computation complicated.
Yes, it's just for hand computations. It's much easier to see it without bias.
So okay. So if we recall this example, we used a single layer to solve like the XOR gate, which is this one. As we saw by the result, it failed. It gave us wrong result. So now we need to implement whatever we learned and use a multiple layer to solve this problem. Like for here, we use this multiple layer. The same thing, we got 3 inputs, but instead of going to one output, we added a layer in the middle, hidden layer. We added like 4 nodes. And first we initialize the weights as any value we want, then we train the networks on the data. We have the same data. Let me go back here. With this data,
How do you know that you need 4, not 3, 5, 10?
you can try it. Try with 2, 3, and see which
So
one.
will one work? Assume
One
not.
hidden layer.
Yes.
No, one node. One node
That's
in
all
hidden
of them
layer.
are getting into one node, and then again
We go
it's like
into one node.
which
I've
makes
never
no
tried
sense
it.
to do,
Yeah.
but why not? Can it work?
I think we calculate the hidden layer based on the output, like how many outputs you have, then you see the nodes that you need for the hidden layer.
You can have any number of hidden
Yeah.
layers,
Yeah.
right?
Yes.
I think
So it's kind of amount of memories that you have technically.
I think in the book they assume this is simple problem because they solve the AND with one layer. They assume one layer will solve the XOR.
So I would recommend go back, not now, at home and try it with different number of hidden layers to solve the same problem. If it is solvable, and if you can get to good enough results with, say, only 2 nodes in hidden layer,
Instead of 4, yeah.
or 3, or really change if I will add like 6 or whatever. The bigger number of nodes really change the error significantly, or it will not change it at all, or it will be even worse error. So this is interesting question, how you choose the number of
I
hidden
think there's an
layers.
equation. I think I saw it when I was doing the deep learning. I think it's 1 over sigma of something by the inputs minus x. I think minus x. And you know how many hidden layers you need and how many nodes
I
you need.
believe that all of those formulas are more rules of thumb,
Yeah.
not really
They
Yeah.
are
calculate the numbers that you need, because nobody really understands all of the interactions
Yeah, it's a
inside
black
of
box.
those layers and what exactly they are doing inside. We have the math,
yeah,
and
they
we
do.
can calculate the gradient descent and so on, but it's less clear what is really going on inside of that memory part.
It's a black box with nobody
Yeah.
knows. It's not.
More try and error, maybe. For, like, we take this exam, let's,
Yeah, that's what I was trying to say. I think one of it is 4 because. Can I go to the-
Sure.
have a
You have
look.
it.
There's some.
Okay, on the simple layer, singular. not
Yeah,
single.
simple. It's simple.
When you have 1 8 here, and then
1 output.
yeah, 1 input. Okay.
Yeah. And 1 output.
Yeah, 1 input, and okay, let's consider a picture, image, and then you have it. Yeah, you have a weight. Yeah, and then the output on the side. If one of the reasons that the bus it is hard, because the bus, like the teacher was saying, the bus is considered as another weight. Because one of the reasons the bus is hard here, it is because, let us consider that you have if the input it is 0, and then if you have that simple linear, equal Wx, you have 0 on the output. So they add the bus as b to have y equal x plus b to avoid that the output be 0 at any time. That is one of the reasons. And then I'm not sure, but yeah, you have 4b, you have 4
Yes.
iron layer.
For the B, this is simple graph. This, as we said, we shift the signal up for the B, for this one. You have this is here. If you add B, you might shift it up. So you start from 1 to 2 instead of 0 to 1.
Yeah, but go back on that picture of the layer.
The 4,
Yeah, yeah. Any one of them. Doesn't matter, any one of them.
here, 4.
Yeah, let's go on 4, 3, whatever.
You know, this, but this is too complicated. This is simple. This is 4.
Yeah. Yeah, they consider that each way corresponds of each input, like each image, and then the 4th weight it is the bus,
Bias.
yeah, the bias. That that is why, and but when you have yeah. I mean,
So,
Maybe.
my thought, yes,
words don't
so
come
if you
to-
add in bias, you get more flexibility in designing
Yeah.
the learning mechanism. This is
Exactly.
true. But what we know about perceptrons and all of those neurons is that basically it's giving like one single unit gives you linear separation. Which means if it is 2 inputs, it's just drawing some straight line And bias is just you getting the
Shifting
line
up and
higher
down.
or lower.
Mhm.
And then one class is below the line, another class is above the line, right? If you put in two neurons, then you put in basically two lines, like two levels. But each neuron in the second layer, which is hidden layer, technically passing one additional straight line and dividing the entire region into multiple sub-regions. Now, like in that case, like exclusive OR, you need two lines to separate the entire region into two layers. So why not to use two neurons in the hidden layer,
Instead of
and why to use four? To me, it
That's
would make
another-
sense why you're using two and not four. Four, you
Yeah,
getting
but
four
for
lines
the
is better
errors-
than two. I mean,
Yeah, but
using four, you can also draw only two lines,
yes.
but two will be basically the same two lines. So you can do that with 4, 6, or 128, or whatever other
Yeah,
number. But the question is two enough?
No.
Why not?
Okay, I don't have an answer. but yeah. I don't have it.
Like, is it faster training that you have like more options and then you have more lines wiggling around until they shape the entire thing, and it's more probable that if you dynamically changing four lines like that, they will outline your region, at least some of them will outline your region faster than if you only moving two lines like that.
Yeah,
On
yeah,
your
it's probably because of the
space.
transformation.
I think we can play with it. I can try to change the weights here. This is what changed the layers
So
in the code.
I don't know the answer, okay?
Yeah.
So it's not that I know
Is it the
the
accuracy?
true answer to
May
that.
accuracy, it's more accurate.
I'm just
It's
trying to
gonna
think
be more
about the
more
intuitive
it's
way.
better.
It depends.
Yeah,
The,
it's
the
gonna
higher
be
the model
accuracy and the
complexity, the worse the trade-off
Accuracy.
between bias and variance. So you have to be very careful with model complexity.
May
So
take a
more
month.
lines you have,
It's more accurate,
more
less error.
it could be more accurate,
It
but
takes a
Could
month.
be.
But
Yeah,
the
it
time,
could be more.
the process time is going to be more. That's
But computationally it's more expensive. And then this is like bias versus variance,
Variance, yeah.
but
which
there
is
no-
like overfitting problem.
Yeah.
You can overfit the data that you have specifically. In the exclusive OR, it doesn't matter because even if you overfit to the data, it doesn't matter. It's fine to overfit to the data in that case. Then something more complicated probably it will not work that great. If you have too many layers
Yeah.
and too many hidden neurons.
So here's like when we implement it, it's gonna work. This check the data.
So
So
the
the four.
one thing that I'm interested in,
I
you
can
do that
change
with two.
We can change it on the.
I can
Instead
change the
of four.
weights.
Yeah, we can change
So 1-1. Is this the exclusive OR? No, this is.
No, this is not exclusive.
it. Yeah, this one.
I think I forgot to change the. This is exclusive OR. I think we were trying something else. I forgot to change it to this one. Here's exclusive OR.
So this is exclusive.
This is the answer.
Yeah.
This is input. If we change it, we get training different network.
Can change
This
it.
is the fourth rule. How many we have?
Two.
Let me see. 2 to how many input? 3.
Three.
Yeah,
Three,
inputs.
2,
2 to 3. Then the next layer we have
2,
2 to 1 to 2. I think 1 to 2.
Yeah.
1 to 2.
Yeah.
Because we have.
So why you have three inputs for exclusive OR?
This is how they have 3 input. I don't know why.
That
I
is
left
like-
the exam. I think if you remove one, it should work.
Yeah.
But they use
Yeah,
the
but then
3
you need-
inputs.
But
Yeah.
then you need to have
More
eight
term.
outputs,
Yeah.
right?
Yeah, they need 2. Yeah, but they use 3 input as one from the book. I don't know.
So it's just
Extra.
XOR between two of the three inputs.
Yes.
Correct.
So one extra, it doesn't have any effect. Basically,
Okay.
one input. I don't know the exact logic they have behind it, but
Is it that constant one with bias?
it could be. Here, training is it's failed. Like this is we get 0.5 for
You
Just
should
using.
two
use
it failed.
Yeah, you should use 3.
And
This
if
is
you try it
0.5.
again-
No, it doesn't fail. If you think like this is
So it's
98,
about-
98,
It's a coin flip, huh?
it's this one is a it's low. Yeah, it's coin flip. The last
50%,
turn.
yeah.
Well, technically it's not accurate, so the
So
error is
if
gonna
you
be
do more
high.
iterations.
More iteration. Let's see. Add 0 here.
More iterations or more epochs? Because those are two
Let's
different
see.
things.
Epics.
Okay, let's see.
Yeah, the
See, did you add more epochs?
Yeah.
So yeah, you increase model
Yeah.
complexity
More,
and the
yeah.
accuracy went down, so you overfit it a little bit there.
Yeah.
So you actually
more
can
training
train.
data. It's
But you
More
need
epochs.
more
So
updates.
more training data,
More
more
training.
epochs.
Yeah.
It depends on the type of model. Some models you can saturate it with training data and it still won't do any good. Some will do better.
This
Yeah,
one
that's what they said. Like sometimes
So
you can
look,
use
it's
just
also technically dependent on your initial point.
initial
Points.
guess.
Yeah,
Yes.
it depends
Might
on
reach
random
faster.
the learning
choice of
rate.
initial weights.
Also, it depends on how much of the training data you have because it's just a lot of knobs you have to get right.
It depends on the application that you want to use.
That
Usually,
too.
yeah. Usually, each application you have to choose different thing, like more layers or
I'll-
less layers.
All this low-level stuff is covered by computational learning theory. It's really, really quick science.
Because what I do know is that in practice, there are two optimization parameters. You have the weight and the bus. Those are the optimization. But
For each
okay,
node,
you
yeah.
also have
But
the loss
you have the
function.
number of nodes, the number of layers. You have a lot of parameters.
Just for
Yeah.
calculation, we put it 0, just to show that's easy calculation. Usually, you have to add the bias, but just for us, because we use simple calculation, we took the. But we can add
Simple
it.
to add.
Yeah.
But the bias is a really important optimization parameter. You have the weight and the bias.
If it wasn't
Those two.
important, they will not add it. That's why they put it in because it's
Okay, in this case,
single-
yeah. Okay.
Yeah.
It'll work. for
I
two
guess
nodes.
this boils down to what we're doing here is an initialization problem. So they have ways to cover this, and when you get to more advanced models,
Yeah.
like they have ways you can just initialize and go. You don't have to
Yeah.
worry about this problem specifically.
Because even on the calculus of the loss function, because all what you are trying to do is to minimize the loss
The-
function.
Yeah.
Error. Yeah.
Yeah, you have error function.
Yeah.
So even on the calculus of the
Error,
equation of
we
the
have
error,
the
you
different
have
formula.
the bus. That is one
Yes,
parameter.
yeah.
So
For simplicity, we use we set it as 0. But we saw like for this one, if you use multiple layer, you might more separation in our classes. Yeah, for multiple layers. I think most people they use singular until the 90s. Like, people kept using single layer up to the 90s.
Well, technically, a single layer will work on every linear.
Yeah, they were trying to
According to Gomarov, yeah.
Because maybe computers they weren't that powerful to solve complicated problems.
multiple.
Well,
A lot of-
some people were using it. Yeah, computers were not keeping up to
as
the
high
task.
as
Yeah.
now, so that's what.
Yeah.
Maybe one person in the whole world have good computer to solve simple things. Then, as we saw, we can change a lot of parameters and we can improve our function. One of the more common method used is the momentum. As we talked about in the gradient descent, like sometimes if you choose big step size, you're gonna miss your minimum here, the global minimum. If you choose too small, sometimes you might get stuck at the local minimum. This is local minimum, which is not the global, which is not the optimized value. So what we can do is use something called momentum, which is basically just a smoothing function, which will keep previous weight change value. Like in here, for this example, this is the previous weight, and this is the new step, or the new, after you calculate the error change, you get this step. So if you use momentum, you see you will reach the local minimum faster, the global minimum, or where you're not going to get stuck inside the local minimum. So this is a good, useful method to use, which is using the momentum.
We use it. That's what we use. Yeah.
Yeah, to avoid some cases like this. It will will reach faster, because we'll keep record of the previous values. It's like a memory effect. and we have like an example. Like we use the same network, and then we can add that term in there, the momentum. If you look, where's it here? Like this term, this is the momentum value in the code. Like back propagation momentum. You added this term to the code, so this will keep record of the previous values. Because we get delta 1 and delta 2 here, so we need those two.
So alpha.
Uh,
So alpha.
Alpha is the gradient descent step size
Step size.
or learning parameter. In gradient descent, you have a parameter called alpha,
Learning.
which is how far you wanna step, like
Okay.
this. This is alpha. Like this is alpha. This is for gradient descent. You find your gradient going this way.
And
Choose big alpha, will jump over here.
Step
Small alpha will be here. In some cases, I think we're taking like optimization class. Like if you choose small, alpha will go here, big will go here. Sometimes it's never gonna converge because if you're alpha choice, you're never gonna reach this point. Yeah. So sometimes it's specific to that application, the choice of alpha. Most people they start with a small value, 0.1 or 0.01, but will take a longer time to reach it. So if you use momentum, you might reach it faster, and we'll avoid the local minimum values. So you're not gonna get stuck in local minimum because of the momentum.
And also they say if you wanna like if it didn't work 0.1 divided by 10. Each time divided by 10. And that's the number to get like if it didn't work the first time divided by 10.
Yeah, divided by 10 is 0.
Yeah.
Yeah.
So that's to get
Well, if you keep, you need to run your value, then it's not gonna work. How are you gonna know? You keep checking it. If you use something simple like momentum, just add in one term to the back propagation or to your algorithm. This will help a lot. Like same thing, we get results over here.
So technically speaking, you could use larger values when you just initially training your network with a few first examples where
See how it
all
works.
the weights are kind of random, and then using fast learning rate because you want to update them as fast as possible. You don't want to update them a little bit, you want to update them a lot. Not too much, because if it is too much, it will jump out of the minimum value at all. But you want to do big steps at the beginning and then to make your steps smaller and smaller when it gets closer and closer to convergence. This is how generally people are training networks. They just start with big step, less than still converging but still big. Okay? And then they get in smaller and smaller steps when they get in closer and closer to the final solution.
So we saw how we implement the momentum. Then I think those last two slides, the advantage of neural network. As we can solve neural network, you can basically solve most problems. So you have a black box, you don't know a model, just put it through a neural network, teach it something like magic. Give you a classification for this. Yeah.
Where you should
Some
be
It's magic.
I don't do magic when I'm sitting there. It don't feel like magic. I don't have a mind.
Yeah.
Magical
Ooh.
So when you don't have a simple model, linear model, or anything representation for your system, you can use it. Neural network will work for that. Yeah. But it has a lot of disadvantages. Like one of them is like it takes a lot of time to learn. You need a lot of data to get an accurate results. Also, yeah, more,
to try.
and you need to keep trying with a lot of parameters to get it to work.
Because we don't know the box that's in there, you have to try and error to get the number that you want. So, but I think they gain better. Now we can calculate most stuff. So
Yeah, I mean, you just need a better computer as well.
Yeah. You always need
You
better.
need to
yeah,
GPUs.
cheaper.
I mean,
It's simple.
Yeah. I think that's it. We can look at the codes if you want. Yeah, look at more codes, change input data. Here's the credits. Yeah. Thank you. Yeah.
We have one thing,
I don't have it.
the history.
History? Why look at history? I took it. Right here, if you wanna do any code, you wanna look anything, change any networks in those. Like we did here, we changed this to 2 nodes. What if we make it 6?
I think 6 would be the same thing.
So
It's 6.
so we got 3 input here. You got 3, then
6.
no, it's 3 input, then 6, then 1 to 6, and make it 1,000. So with less epochs, we were able to train the network. Yeah.
More layers.
If we had more layers, more nodes, we need less data to train it. This is 100. I think it's not gonna work in 100. No, it didn't work with 100. We need more than 100. Yeah, we need like 1,000.
General sets for machine learning in neural networks starting in thousands.
1,000. Yeah.
Not many things you can actually learn from just a few hundreds of examples, which looks obvious for humans. Like
Yeah.
if you will show
10
me
examples.
100 examples of something,
Yeah.
I will be fine with identifying similar things.
Yes.
But in machine learning, it's completely tiny number,
How about deep learning? We can
especially for deep learning.
yeah, you need more data.
For deep learning, you need thousands of millions
Yeah.
of examples. But you can do transfer learning, which is very nice. Again, I recommend to everybody to do that course in deep learning, which is available for free in Mental or our Wall of Fame.
Deep learning,
Deep learning
if you're doing classification,
fundamentals or something like
the
that.
more categories you have, the more data you need. If you
Yes.
have,
So if you have only a few categories, you don't
you
need
need
much.
millions.
Million.
If you have 10 like MNIST, you don't need that much. If you're doing 2, it's a pittance.
But we still have the problem of overfitting, that's right, on deep learning.
True, there are ways after you do hyperparameter tuning, then you can do data augmentation. That'll increase your sample size and reduce overfitting. As long as and that allows you to handle that problem without increasing your model complexity, which would increase your chance of overfitting.
Well,
I
this
think we
is
calculate
not
with
always
the
true. Not for any problem it's true. Why? Because augmenting of the data sets that you have dependent on the type of augmentations that you are doing.
And the type
Now,
of data.
artificially you're introducing some specific types of transforms in the data.
Mm-hmm.
And you basically preferring in your learned network that kind of transforms, which might or might not be real ones that you will see in real world, right? So you clearly will not see any other types of backgrounds, for example, or you will, which are also part of the learning process, right? You will not see any other non-linear transformations on the image which are completely natural for real images.
Mhm.
You will not see any occlusions which are natural occlusions and not artificial occlusions. So all kind of models for occlusions exist, and technically you could use all kind of simple occlusions like occluding part of the image from all kind of sides, or rotating the image or scaling the image. So most of the augmentation is very limited in the types of the transforms that you are exploring
Right.
for natural reasons, because you cannot
Exactly.
predict what will
You
really
could,
happen.
for example,
to
if the original
thing.
data is to 2D occluded cat, you can't really augment data that then creates a different perspective of the cat.
Yes.
There are networks models that are being developed that could probably help with that, like capsule networks. But right now, yeah, that is a problem. Of transformation only goes so far. I mean, augmentation only goes so far.
I have one question. If we calculate the error, can we know how many data we need? Input data?
That is my
Yeah.
research project.
Yeah.
That is a standing
Example
problem
of
in,
your PhD role.
in all of machine learning is how much data do you need to mature a network to get a certain accuracy. There are certain type of techniques you can find out, but does it generalize to any architecture, any model, any type of data? In some instances, you can try to find out using trial and error to see, like
Yeah,
the
to
evidence to
see
see how much.
error.
But then, is that transferable over to something like ImageNet, where you have 1,000 classes and you have millions of data points? You have to find a way to generalize that into a domain where you don't have enough data and you really can't test it, and hopefully it's accurate. So that is a standing problem. If you can solve that, you will be rich. Because, for example, in biomedical imaging, it might cost lots of money to get more data. So it'd be great to know. Oh, I have these 10 sets of CTs. How much accuracy will I get with these 10 CTs? How much more will I need, or do I have enough? It's easy to find out if you have enough, and plus, then the accuracy depends on your model.
The only thing we can plot the error. That's right.
Well,
So we can adjust,
even
yeah.
you cannot say if you have enough, because you could be locked in the local minima, and then this is your error, and it's not getting lower because you are somewhere in the local
Yeah, it
minima
really
stuff.
depends. Did you do your hyperparameter tuning correctly on this architecture? And then when you start training it, I reached the maximum accuracy with this architecture. What do? Do you increase the model complexity? Do you get more data? Do you do better augmentation? Where is it? Is the network mature enough? There are many ways you can try to slice this onion. You still get layers of complexity.
And also, I have a general question. Why we test on the same data that we train on? Usually, people they
You
test.
don't?
Yeah, usually just the first initial. They take the same data to see that
What-
See the
If you
performance.
do something like
Accurate.
K-fold cross-validation, technically you see the same data, but then you're doing trials of model testing.
Yeah.
It's different. Like if you're doing a simple train test split, your testing data is never seen in your training data. If you're doing train validation test, then you would take your training data and split it into
Yeah.
train and validation. Your validation is never seen in your training. K-fold cross-validation is almost like I forgot what it's called.
Same thing. We
Something
use for
else,
the-
but yeah, it sees all the data, but it's never training a model on the training data and on the validation data it sees in the training data. You train like separate models for however many folds you have, then you look at the results. So you would never want to put any type of test or validation data in your training data because then it's perfect. It's
Yes.
like memorization.
So look, when you're talking about this, for example, you don't have much choice. You have only 4 kind of outputs,
Yeah.
right? You have like 4 kind of inputs and 1 output.
You need to
which
check
support
it with
results.
it.
Yeah.
4 possible inputs. So it's not much play here that you can play with, that you have to put aside 20% of the data and never touching it. You have only 4 inputs total, right? So nothing to play with. But in other cases, in real cases where you have variability within the data and different kind of answers to different kind of questions, which means like you have tons of different inputs and you have tons of different possible outputs. Then you can put 20% of the data aside, never touching it in the training process. Training on the other, training and validating on other 80% of the data to get less overfitting with validation. So validation gives you opportunity to train your data without too much overfitting, because this is what it is built for. And then you're training on those 80% of the data, and you don't really care what will be the error on that data. Why? Because it could be perfect, like 100% precise, great,
Yes, that's-
but it means nothing.
yeah.
It's just fitted to your specific training data. That's good, but this is not enough. The only error which actually matters is the testing error on the testing set which you put it aside. This is what matters. Everything else, it's good that you have like low error on training, because if your error on training set is very high, it means that definitely it will not work on testing data. It's not even working on your training data, right? So your model is not sophisticated enough. So you need more layers, different parameters, different whatever. You need something else. You need to change your network. But if it is great on training set, it means nothing in regards to the testing set. And this is what matters.
You remember you were at the MATLAB thing. You
Yeah.
remember when he was talking about the salad, and they had the training data, which was very perfect. And then people took pictures and tried to fool them.
Yeah.
And he came up with like a
78%.
whatever type of salad it was. It was just looked like French fries, and he predicted it's French fries. It has to be, your network has to have a really low generalization error, and so you have to, if you did like, oh, I'm 95% on predicting
That's what he
whatever
did.
rabbits in my
95%.
training and validation, and then suddenly someone tries to trick it.
Yeah.
There are methods and whole domains about trying to.
I think they put carrots similar
Yeah,
to
French fries. Yeah,
So the accuracy went down to 78%.
yeah.
People try it.
Although you just consider those outliers, you have to watch for those. Or, in some cases, it could be nefarious intent. You can try to fool the network in such a way and make it think one thing when it's actually another. And there are whole groups of people trying to be able to fool neural networks that way.
Okay.